All right, welcome to a new week. So we're going to continue with these slides on number theory and encryption, and we are starting to get to the good stuff. So I'm excited for us. We stopped last time after discovering this thing called the Euclidean Algorithm, which gives us a way to take any two numbers, any two integers, that is, and find the greatest common divisor of them. It's an algorithmic way. It gets to the answer very quickly, and all you have to do to calculate the GCD of some x and some y is to replace that with trying to calculate the GCD of y mod x and x, okay? So all these numbers, they eventually just keep getting smaller and smaller until you end up with trying to calculate the GCD of 0 and some number, and we have figured out through reasoning that the GCD of any number with 0 is always just that other number, okay? So that is the trick. That is the Euclidean algorithm, and it was invented way back in the day. It's sometimes called like the very first algorithm that ever existed. So let us get some practice with this, and I'm going to give you an example of calculating the GCD of 80 and 61. So let's do that, and we're eventually going to program the whole thing in Racket, but let's just get started with calculating the GCD of 80 and 61. So the way I'm going to do it, the way I'm going to write this is because eventually we're going to like shift around x and then y to be y mod x and x. I'm going to write y first, okay? Because of the way that's about to happen. So it's like I'm going to write y, then x, and then we're going to do y mod x. And then suddenly this is going to be the new y, and this is going to be the new x. So it's just going to keep on being backwards. If that makes any sense at all. I promise it will. So I'm just going to write the y first. Okay, so we're trying to do GCD of 80 and 61. And let me write that a lot more pretty. So this is the x, this is the y, and I'm just going to write the y first. Okay, so y equals, that's the 61. X equals, that's the 80, and then y mod x. So the reason that I'm doing it is because, like, yeah, we're trying to divide it. Okay, y mod x is 61 mod 80. Well, that one's pretty easy because you can't divide anything. So that's just, I actually did it before. Modulo 61 by 80. Well, yeah, it's just 61, right? So that's the answer. So that's just 61, and now they flip-flopped. Okay, that's the idea. We want the smaller number in the y spot. So now, watch what happens. This is the weird thing. All these kind of go away. I'm going to maybe use a different color just to show you what's happening here. It's very interesting. So this one's like done. This one is the new y, and this one is the new x. Do you see that? Because we need to replace it with y mod x. That's the x position, and this is the y position. Okay, very odd, I know, but hopefully this is making some sense. So now we have y mod x being our x, and then y was the old x. Yeah, so they flip-flopped. Now we're trying to calculate the GCD of, what is that? 61 and 80. So eventually it's going to make it so that the smaller number is the x. That's what's happening. That's just how the algorithm is working. And so now let's calculate the new y mod x. What is that? So that's 80 mod 61. That's going to do something. Modulo 80, 61. Bam. 19. Yeah, that number got smaller. Very, very good. Okay, so now we have 19. And I'm just going to keep it blue, and I think you see what's going on now. The reason I'm writing it like this, because now it's just this one, and I'm going to replace it with this one mod this one. Yeah? So it's 61 mod 19 now, because now we have to calculate GCD of, this is the x, this is the y, 19 mod 61, so we're going to calculate 61 mod 19. Okay, so maybe I should write the chain of all this stuff. The GCD of 80, 61 is equal to the GCD of 61 and 80, which is equal to the GCD of 19 and 61. And so now here we're going to write whatever 19 mod 61 is, oh sorry, it's the other way around. 61 mod 19. I'm confusing myself. So it's always the upper number mod the lower number. Okay, so 61 mod 19 goes there. And that's 4. So see how the numbers are getting small very quickly? That's wonderful. So now, well, that's equal to the GCD of y mod x, which is 4, and the old x, which is 19. And so again, I'm going to do 19 mod 4, which is 3. Very nice. Bam. So that's now GCD of, what do we got? We've got 3 and 4. Okay. And then we're going to do 4 mod 3. Until we find 0. Oh, that's 1. Dun dun dun. 1. So now we're going to calculate the GCD of 1 and 3. And we're almost there. So we're going to do 3 mod 1, right? Upper number mod the lower number. And that one's 0. So now we found 0. Okay? So that one's 0. That's when we stop. Okay? 1 is like our last number. And the reason we stop is because we're now trying to calculate the GCD of, well, 0 and 1. And bam, we got to this. And the GCD, after all of our hard work, it ends up just being 1. And that is the final answer. The last non-zero number in this long chain of things is our answer. Okay? So it just so happens that these two numbers don't share any common divisors other than 1, which means they are relatively prime to each other. That's the word. And actually, is 61 itself prime? Because that could be the reason. I'm not really sure, but that might be the answer there. Okay? So that is the GCD of 80 and 61. And I couldn't resist, so I stopped the video and asked, is 61 a prime number? And the answer is yes. So that's obviously why the answer is 1. It's prime. Okay? So now I would like to program this in Racket. That's not too bad, I think. It's going to be just a recursive algorithm that stops whenever we get to 0 at the very end. Okay? So let's do that, and that'll be that. So let's make a file called gcd.racket, and let us begin. So there we go. So we're going to define a function called gcd, and then we have x and y, of course. And this is a very, very simple algorithm, because, watch all I have to do. Oops. Whee. All that I have to do is say, okay, gcd_xy, well, it's just whatever y mod x and x is, unless we have 0 as x. So let's just check x. Okay. Cond, bam, is x 0. If it is, then the answer is y. You see that? If x is 0, the answer is the y. That was the second thing that you gave. Cool. Otherwise, oop. Else, we're just going to give back the GCD of y mod x and x. It's a very simple algorithm. You see that? Bam, bam, bam. See if it's happy. Looks to be so. And now let's run it. So let's go to Racket. And all of our fancy hard work was not all for nothing. It's going to be very useful in a second. But now we can just say GCD of, what was the first one? It was the bigger number first. Yeah, 80 and 61. Bam. And wow, it's 1, so we did it right. Very, very good. Okay, so that is the GCD. That is the Euclidean algorithm. It's only 3 lines of Racket code, and it's probably 3 lines of C++ code as well. It's not too bad. Okay, so that's the Euclidean algorithm. Now I want you to try it yourself. Okay, so find the GCD of 42 and 30, please. Okay, so try that. And assuming you have come back and you didn't cheat, let's see what's going on. And now your book, it writes it from left to right, and we're going to start doing that too, because I just did it this way because I didn't know if I'm going to need room. So I just did it from top to bottom, but let's do it from left to right like your book does now. So this is the x, this is the y, and we do the y first for reasons. 30 and 42. You know that they're about to swap because it's eventually going to make sure that the smaller number is on the left side. Okay, that's the way the algorithm works. So we got 30 and 42, and so we're going to do 30 mod 42 and get the answer right here. 30 mod 42, what is that? Bam, that's just 30 because when you're dividing by a bigger number, it doesn't really work that way. Okay, now we can do 42 mod 30. That's very nice. 12. Okay, 12. Now I can do 30 mod 12. And it's 6. Okay, okay. Now I can do 12 mod 6. Ooh. Hey, hey. And that one is 0. We don't tend to write the 0. This is our answer. Okay? That's how you do it. So that is the GCD of 42 and 30. They share 6 because you got 6 times 5 and 6 times 8. Yeah? I believe so. Or no, 7. 7 is 42, isn't it? Okay. So now we have the GCD under our belt. We are professionals. And with that, here is a quick break with some comic relief. All the pictures of Euclid show him very, very angry, or maybe he's just very intensely doing his work. Okay, so everyone meet Euclid, and let us continue now. So we have the normal Euclidean algorithm that we know and love now. There's also a way to extend it. Okay, it's called the extended Euclidean algorithm. Mathematicians have very obvious names of things. Okay, so what our goal is, and I promise this is going to be useful soon, is taking the result of GCD x and y, maybe it's 1, maybe it's 6, we can represent that as a linear combination of x and y themselves, which is quite nice. It's a fun little quirk that you can be able to do that, but I'm going to show you exactly why and exactly how. So, formally, this might make more sense actually formally, if x and y are integers, then there are integers s and t, so 2 integers, they can be positive, negative, doesn't matter, such that the GCD of x and y, those original integers, equals a linear combination of x and y. So x times s and y times t. Okay? Hopefully that makes sense. And this is going to be very, very useful for RSA. Okay? That is the encryption algorithm that we're going to talk about soon, and this is one of the key pieces of it. Okay? So that is what we want, and we can use what we already have to get started. Okay? We can extend what we already have, the normal Euclidean algorithm, to make this happen. And we're going to just end up working backwards from all of our scratch work. So like, okay, we ended at 6, let's make 6 into a linear combination of 12 and 30. Okay, we have that, let's make 12 as a linear combination of 30 and 42. And then it all works out. Okay, I promise. So I'm going to show you that. And the secret sauce is the division algorithm. So each time when we're doing modulos, we have like something that we're taking the modulo of, like it's always y mod x. So we pretend that we're dividing y by x, because we're pretending that n is y and d is x. And then we're ending up with the remainder and kind of just forgetting about the quotient, right? That is the idea. But that's going to give us the ability to solve for these integers, okay? If we just keep this in mind. So without any further ado, let's have an example of 675 and 210. So you know what's going to happen every time I do this. If this is x and this is y, they're gonna flip-flop until y is smaller than x. So we have our x, we have our y. I'm going to write the y first. So 210 and then 675, and then if we do that mod that, it is immediately 210. And so now we can do 675 mod 210, because this is our new y, this is our new x, remember. Okie dokie. So let's go here. I did the first one just to make sure. Modulo, now we do 675 mod 210. Okay, so that's 45, and so now I do, might as well just keep writing it. 45, this is modulo, modulo 210. 45, that's 30, and then we do 45 mod 30. And that's 15. Very, very nice. And then we do 30 mod 15, but I think you can see that that's going to be 0. So that is our answer. Our final answer is 15. And now here's the trick. This was y. This was x. And maybe I'll use different colors. This was y. This was x. So let's use this division algorithm because watch what happens. Dun, dun, dun. What we were doing is, okay, yeah, our number that we are trying to divide, that was our y, so we have our 45 equals, okay, yeah, that's 30 times something, 30 times the quotient. I guess I should do the quotient first, so something times 30, which was, well, what's the divisor of that? That's going to be y div x, or 45 div 30, which is 1 because it goes in one time, right? If we do, we get 3 halves, but unfortunately that's not good enough. Integer division, please. 45 mod 30. Oh no. 1, okay. That's what I'm trying to say here. So that's 1, which is quite nice. So that's 1 plus the remainder that we found, and that is 15. And we can solve for the 15. We can solve for this whenever we wanted to. The answer is always going to be, dun dun dun, it's y equals, let's see, q is y div x times x plus the remainder, which is y mod x. And then we can solve for y mod x. Okay, so let me maybe move these down, because that's the trick. That's the trick, and we can do this backwards. Okay, so we do this. Y mod x equals, we just bring all this to the other side. It's, well, it's y minus y div x times x. Okay, so then from there we can do this. We can go from this equation to, well, we didn't even have to write it really. We can go from that to, okay, yeah, it's 15 equals the original y, which is 45, minus 1 times 30. Okay, and hey, that checks out, makes sense because it's the division algorithm. But this is our beautiful thing that we're using, this fact. Whee! Okay, so now we found 15 out of 45 and 30, and we can just work our way to the left. Okay, so now I can make 210, or sorry, now I can make 30 out of 45 and 210. Okay, that's where I'm going with this. So now 30 equals, apparently, well, it's going to be y, which in our case is going to be the 210 now, because all these are shifting. It's 210 minus, what is 210 integer divide 45? That is 4. It goes in 4 times. And that is times 45, of course. Which makes sense, and that's the remainder. 30 is the remainder after that. Okay, so now we've solved for 30 based on 210 and 45. So let's keep on going to the left, and let's solve for 45 in terms of 675 and 210. And we can stop there because they just flip-flop at the end, and they're the same numbers. Okay, so now let's solve for 210. no, sorry, 45. 45 out of 210 and 675. So what's the y? This was the y and this was the x, right? It's 675 minus something times 210. How many times does 210 go into 675? Without anything left over is 3. Minus 3 times, and that was the 210. Okay? So apparently we can go in that many times because then we get like 630, and then we have 45 left over. Okay, that's making some sense. And I have a stray circle, sorry. So with these, look what happens. I can start plugging things in because here I have the 15. I need to express 15 as a linear combination of 675 and 210, but I can get there because I can replace the 30. I can replace the 45. It's all going to make sense. It's all going to work out. Okay? So let's go backwards. Okay, 15. We take all this, take this work, and that is going to lead us to the final answer. And this is going to get kind of ugly, so I paused the video, made a new slide for us, because I would like to copy all of this, and oops, we'll work on that slide. Okay? If only it would let me select the entire box. Let's do it this way. There, okay. Now I'm happy. So, here's what we can do. Go here, please. I don't need the arrow. Thank you. Are we recording? Yes. All right. So, watch what happens now. I can take my 675 and I can take my 210 and eventually, through these equations, get to 15. Let's start with 15. So 15 equals 45 minus 1 times 30. And this is all going to go away because I know what 30 is and I know what 45 is. Oh, so what is 30 but this stuff? And ooh, that has a 210 in it. We're getting closer to the answer. So I'm going to replace this 30 with what I know 30 to be. Okay? So I'm going to replace that, which equals 45 minus 1 times 210 minus 4 times 45. Oh, all right, that equals 45 minus 250. Did I write 215 somehow? Yes, I did. Excuse me. Too many numbers, apparently. All right, that's 210. Thank you very much. 210 plus 4 times 45. So that is apparently 5 times 45 minus 210. And then we can play the same game, because now we know what 45 is, and ooh, that's in terms of what we want. So let's just replace this 45 now with what we know it to be. There. So that's 5 times 675 minus 3 times 210, which is then subtracted by another 210 out here. So distribute 5 times 675 minus 15 times 210 minus 210. And one last time, that is 5 times 675 minus 16, right, times 210. And before we do anything, let's make sure this is right. Okay, 5 times 675. Because I did my math wrong and I had to edit the video. Minus 16 times 210. And hey, that's 15. I'm happy about that. Okay, so we got the answer. And that was what we wanted, because here is 675, here is 210, and here is 15 on the other side of the equality. We found our s and t. We found our s, we found our t. It is 5 and negative 16. And that gives us our GCD. Okay, so we worked backwards. It was a long, horrendous process, but you can write an algorithm for this, and that is the topic of your lab, of course. So, all is well. We found those answers, and hopefully, with enough practice, it will make a lot of sense and it won't be too bad. Okay, so that's how you find those integer numbers that can make a linear combination with your original x and y to find the GCD, okay? And this will eventually be useful, I promise. All right, so that is everything that I wanted to say about the extended Euclidean algorithm. Maybe I should move all this stuff down so it's easier to look at. And from now, let us move on to an example where it's your turn. So I'm going to give you simpler numbers, 42 and 30. So not 45 and 30, because we already did those, but 42 and 30. Try those, and represent the GCD of these two numbers as a linear combination of the two. Okay, so give this a shot, and then we'll do it together. Okay, so we got 42 and 30, and we're going to do our, like this is x, this is y. We're going to play our game, right, in the y first, like 30 and 42, and honestly, they're going to swap. So let's forget about this, and forget about that 30. It's 42 first, then 30. Why not? Then we're going to do 42 mod 30. What is that? I'm going to cheat and not use Racket for once. It's 12. 30 mod 12 is 6. 12 mod 6. And that should be 0, right? So the answer, the GCD of 42 and 30, is in fact 6. And let's work our way backwards. So, using this fancy idea, the remainder equals the original number minus the quotient times the x times your divisor. All right. So, again, this is like the y, this is the x, this is the y mod x. So y mod x equals 6 equals y, 30, minus y div x, so 30 div 12, so 12, 24, right? So 2 minus 2 times the 12. Okay, and this makes sense because that's the remainder. It goes in twice, and we get remainder 6. All right, and then we'll do it for the 12. So 12 in terms of 42 and 30. So 12 equals 42 minus, well, it's just 1 times 30, right? 1 times 30. And then we do it for the, oh no, that's the end, because these are the other two numbers, and there's the 42 and 30. So what we can do now is just bring these together. We want some combination of 42 and 30, and we want to have 6 on the other side. Okay, so we're going to start with the 6. Start with 6 equals, so I went from there to there, and then we're going back to here. 6 equals 30 minus 2 times 12. But what is 12? Well, it's that. Okay, we can replace that 12 with 30 minus 2 times 42 minus 30. Okay, which equals 30 minus 2 times 42 plus 2 times 30. Okay, so now that's 3 times 30. 3 times 30, and minus 2 times 42. And apparently, hopefully, that's going to equal our 6. Okay? So the 3 and the 2, hopefully, do the right thing. So we have 3 times 30, that's 90, minus 2 times 42, that's 84. Yeah, cool. So it's 6. And that gives us our original numbers, a linear combination of them, making the GCD. Okay? So I promise this is not all for naught. And you will soon see the reason. Okay? And the next step is through multiplicative inverses. And this is something you already know how to do now because we know the extended Euclidean algorithm. So a multiplicative inverse, mod n of a number. It's a very long word, but it's going to make sense, I promise. So remember that like an inverse of a normal number, like, I don't know, 4 inverse equals 1 over 4, right? Such that, and the reason that these are inverses is because 4 times its inverse, 1 over 4, it equals 1. That's what an inverse means. You multiply them together, you get unity, 1. Okay? So a multiplicative inverse, when you're doing mod n as well, is an integer that is non-zero, but it's mod n, and it equals 1 when you multiply. Okay? So if you want to find the multiplicative inverse of x mod n, you find this s such that s times x mod n equals 1, okay? And this is not quite the same because you can't really do fractions in integer land, but you can still find multiplicative inverses when you're doing modulo, which is very fun to think about. And we don't have to do any extra work. We can use the extended Euclidean algorithm to find this inverse, okay? It's not going to be a problem. So we can just stick x and n, these two numbers that we need, into the GCD and pray that we get 1, because that's the only way that there's going to be an inverse. If you get 1, done, 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 because of your extended Euclidean algorithm, you can find numbers s and t such that s times x plus t times n, we give x and n, those are the important ones to give, such that those equal 1. And oh man, you can now take mod n of all the sides of this equation and watch what happens. The n's go to 0. Anything times n, like I was saying, I don't know, like 2 plus, I don't know, 42 times 5, mod 5, well, that's going to be the 2, right? Because these go to 0. This is the same idea. These go to 0. Okay? So we're left with sx equals 1 mod n, and that s is the multiplicative inverse. Okay? Dun, dun, dun. S mod n, in fact, is the multiplicative inverse, because maybe the algorithm gives you back a very large number, which was unnecessary. Okay? We want it to be within this range. That's all. Definitely can't be 0, though. So that is the multiplicative inverse of x, and that's beautiful. So let's find the multiplicative inverse of 7 mod 10. How do we do it? We just do the GCD of 7 and 10. Okay? That's wonderful. And I'm going to write the 10 first, then the 7, and then we're going to do 10 mod 7, which is, I think, 3, right? I don't trust myself, so let's just do it. 10 mod 7, yes, it's 3. And then 7 mod 3, that's 1. I trust myself enough for that one. 3 mod 1, well, 1 goes into everything. And oh man, yes, the answer is 1. So we are able to find a multiplicative inverse. It exists. Oh man, oh man. And now we can use our fancy equations. So again, 1 equals 7 minus 2 times 3. So you see how I did that a bit quicker than usual. Then we have the 3 equals 10 minus 1 times 7, which is just 7. Okay? So those are the equations that I need to find the those two numbers, s and t. So let's bring those up over here. And let's say, okay, yeah, 1 is equal to 7 minus 2 times 3, but I know what 3 is. I'm going to do this. 7 minus 2 times 10 minus 7, hey, which is equal to 7 minus 2 times 10 plus 2 times 7. So that's equal to 3 times 7 minus 2 times 10. All right, let's confirm this. Let's make sure it's 21 minus 20. Yes, that's 1. Cool. And so that means whatever number that was next to you, because we're taking modulo here, we're going to mod by the 10. So this is going to go away. So that's going to 0 once we do mod 10. Okay? So now we have 1 equals 3 times 7 minus 2 times 10. And we're doing all this mod n on both sides. So this goes to 0. And 3 is the multiplicative inverse of 7. Okay? 3 is the answer. That is the goal. Okay, so we found our 3. And let me prove to you that that is the multiplicative inverse of 7 mod 10. Because, watch what happens. 7 times 3 equals, what is it? Well, it's 21. And when I do mod 10, oh man, that's 1. How weird. It's a fraction that ends up being the real inverse of a number. That's really weird. But, oops. But it works. It's another integer that ends up being the inverse of a number, because modulo land is odd. Okay, so that is how you find multiplicative inverses. And now I want you to give it a try on your own. Okay, so let's have this example here. Let's make sure I'm still recording. Yes. So I want you to find the multiplicative inverse of 35 mod 48. So you're going to find some number such that, so that is, find S such that 35 times S mod 48 equals 1. Okay, that is the idea. That's what we want. That is an S, not a 5. I'm confusing my own self. Okay, so that's what I want you to find. You will use the extended Euclidean algorithm, of course, to find those numbers, and then you know that hopefully it's 1. If it's 1, then you can just mod the equation by the 48 on both sides and end up with what you wanted. Okay, so give this a try, and then we'll do it together. So the multiplicative inverse of 35 mod 48. Let us figure this out. So again, we're going to use the GCD algorithm at the very beginning to figure out these numbers. So 45 and 35. Oops, 48 and 35. Digits are not my strong suit, apparently. 48 mod 35 now is 13. And 35 mod 13 is 9. 13 mod 9 is 4. Go back. Is 4, and then 9 mod 4 is, I believe that's just 1, right? It goes 8, and then 1 more makes 9. So yes, it's 1. We get the 1 at the very end. And now it's our job to use these equations again to get them back to 48 and 35. So we have 1 equals 9 minus 2 times 4, because that's the division. That's the quotient. 9, 2 times 4. That makes 1. And then we have 4 equals, in terms of 13 and 9, 4 equals 13 minus, that's just 1 times 9, right? So it's just 9. And then we have, 9 in terms of 13 and 35. Equals 35 minus 2 times 13, right? It's going to go 26, and then you have the 9 left over. 2 times 13. And then we can finally do 13 in terms of 48 and 35. And that just goes in once, right? Yeah, minus 1 times 35, which is just 35. Okay, so now, again, we're going to start with this and then work our way down to having it in terms of 48 and 35. Okay, so I'm going to do it over here. Maybe I'll use a different color for fun. 1 equals 9 times 2, or 9 plus, 9 minus. What in the world? There we go. I will eventually catch myself. I'm sorry if you're yelling at me through the screen right now. It's a lot of hardcore math, and it has to be precise during a lecture. Okay, 1 equals 9 minus 2 times 4, but we know what 4 is. 4 is just 13 minus 9. So 13 minus 9, and so we can eventually bring these together. So that's going to be plus 2 times 9 and another 9, so that's simplifying as we go. 3 times 9 minus 2 times 13. Okay. 27 and 26, yes, as a sanity check. And now we know what 9 is here. We can bring in the 9. Equals 3 times, and 9 is just 35 minus 2 times 13. 2 times 13. And then again, minus 2 times 13. So that is equal to, okay, how many 35s? 3 35s. And then how many 13? So we have minus 6, and then minus 2 more, so minus 8 13s. Let's make sure I simplified properly. 3 times 35 minus 8 times 13. Cool. All right, now we know what 13 is. So let's bring that in. 3 times 35 minus 8 times, what's 13 is 48 minus 35. So how many 35s is this? We have plus 8 of them. So 11 35s minus 8 48s. Okay, and I think that's the answer. So 11 times 35, we can always check ourselves, minus 8 times 48. Yes, that is 1. Okay, so now we have these numbers. We found their coefficients. We found them equal to 1. And because we're doing mod 48, we will know that this is going to go away. This 48 is going to go to 0. And so the 11 is our answer. And that is within the range 1 to 47. So that's already golden. So 11 is our answer. And we can confirm that. Okay? We can always check ourselves because 11 times 35. No, that's too bright, sorry. 11 times 35 mod 48. That better equal 1, okay? That equals 11 times 35, which is 385 mod 48, which better equal 1. And bam, it does. So, if you multiply 35 and 11, you get back 1 in mod 48 land. And that is the multiplicative inverse. Okay, so I think that is all I wanted to show on this slide. Hopefully you got that. It is a bit of work, but it will be fruitful, I promise. Once we talk about RSA, this is very, very key in making RSA work. Okay, and so now I think maybe we'll have one more slide and then we'll get out of here. Okay, we'll do the rest next time. So, number representation. This is very fun to talk about if you haven't learned it before. If you have, we're just going to strengthen your knowledge, okay? So let's talk about numbers. So the number system that we like to use in our day-to-day life is called decimal, just in case you forgot, but it's also known as base 10. That's the technical term. And the reason why is because it has 10 digits total. So the valid digits in base 10 are, well, 0, 1, all the way to 9, right? The second you get more than 9, you want to add 1 to that, you have to add a new place, a new decimal place. So that's why we have 10 digits total. This is called base 10. So if I had base 5, how many digits am I allowed to use? So for base 5, it should be, well, you have 0, 1, 2, 3, and 4. You have to stop at 4 because that's your 5 digits. And if you try to add 4 plus 1, you get 1, 0. You have to have a new place in base 5. Okay? So because I'm going to talk about a bunch of different bases, I'm going to use subscripts to say which one I'm talking about. So, for example, 42, subscript 10 means 42 in decimal. Okay? 42 in base 10, that's the base. Okay, so to get you going, let's talk about how to break down these numbers, because that's going to be the secret for converting from any other base to decimal. You remember in grade school how you broke down 1,234 base 10 using decimal expansion? Well, you did something like this, right? 1, 2, 3, 4. Well, that's equal to 1 times 1,000. 1 in the thousands place plus 2 times 100. 2 in the hundreds place. Plus 3 times 10. That's the tens place. Plus 4 times 1. That's the ones place. And maybe once you got in a fancier math class, it was more like, okay, this is 1 times 10 to the 3 plus 2 times 10 squared plus 3 times 10 to the 1 plus 4 times 10 to the 0, which is 1. And this is the secret. This is how you can convert between arbitrary bases to decimal, because all you have to do is swap these bases out. You see where the base is being used? Right here. So if you just swap those out, you can expand in any base b. Okay? So let's figure out what 1, 2, 3, 4, those are valid digits in base 5, what 1, 2, 3, 4 base 5 is in decimal? Okay, let's figure that out. Well, 1, 2, 3, 4, base 5, that's equal to, well, we're going to work from right to left. Okay, this is 4 plus 3 plus 3 plus 1. So 4 times, and then it's the base to the 0 power. Okay, 4 times 5 to the 0 power plus 3 times 5 to the 1 plus 2 times 5 to the 2 plus 1 times 5 cubed. So that's equal to 25, or no, a lot more than that. Let's just do it out. So we have 1 times 5 cubed plus, I'm doing this in Python for fun, 1 times 5 cubed plus 2 times 5 squared. The 2 stars in Python are the to the power of operator that exists. Plus 3 times 5 plus 4 times 1, right? So just 4. And so this is 194 in base 10, because we did base 10 arithmetic on this side, and so then we ended up with a base 10 number. So base 5, it's got a, you need 4 decimal places, or 4 base 5 places to make a 3-digit number in decimal. Okay, so that is how you go from any base to decimal. Okay, that's what you do. You just use the expansion, starting with the base itself to a certain power. So look where the base is. That is the key. Okay, so we can do fancier bases, of course, and I will talk about that in the next lecture. So I will see you there.